Read AI.
Hi, everyone. Just waiting a minute or two just for people to join the meeting. Hi, everyone. Thanks for joining us today. There we go, I think. See if there's anybody else coming in. Okay. I'll get started. So hello, everyone. Thanks for joining us today. For those of you who don't know me, my name is Sophia Alva. I'm on the marketing and business development team at Process Ecology, and I will be moderating today's webinar. Today, we will be discussing how we can generate more value from existing plant data that we are already collecting using process intelligence. So this includes finding hidden operational insights, identifying root causes faster, reducing engineering workload, and uncovering opportunities for emissions and efficiency improvements. So as many of you know, the industry is moving towards continuous monitoring requirements with methane regulations requiring continuous monitoring at facilities by 2030. While that may seem several years away, we all know how quickly these changes can arrive. Many operators are already evaluating monitoring technologies and determining how they'll meet their future compliance requirements. But we'd also like to challenge the idea that continuous monitoring should not simply be viewed as another regulatory obligation. The reality is that collecting more data isn't the hard part anymore. Most facilities already generate an enormous amount of operational data every day. The real challenge, and you could also view it as an opportunity, is understanding what that data is telling you and using it to make better decisions. Every emissions event has a cause, whether it's process upset, changing operational conditions, liquid slugs, equipment limitations, or control issues. So simply knowing that emissions event occurred doesn't tell you why exactly it happened or how to prevent it from happening again. So that's where process intelligence comes in. By combining continuous parametric monitoring with a high-fidelity process model, we can move beyond simply detecting emissions. We can understand how the entire facility is behaving in real time, connect the process events to emissions events, identify the root cause, and provide actionable recommendations that improve both environmental and operational performance. So our goal today is to show you that continuous monitoring isn't just about meeting regulations. It's about unlocking more value from the data that you're already collecting and using it to operate your facilities more efficiently and more reliably. So joining us today, we have Alberto Alva, our CEO. He brings over 25 years of experience in chemical engineering research and process optimization for sustainability in the oil and gas sector. We also have Gabe Matias, one of our engineers and software developers with a background in chemical and software engineering. He focuses on developing advanced tools for emissions tracking and process optimization in the oil and gas industry. He is our lead developer of RTX, integrating first principles modeling with SCADA data to improve regulatory compliance and operational efficiency. Alberto and Gabe, welcome.
Yeah, thank you. Thank you. Thank you, everybody, for joining. Great to be here.
Thanks.
So now Alberto and Gabe will go over their insights. During the presentation, please feel free to submit any questions that pop up. There is a Q&A box just in your top menu bar. So if anything pops up while they're speaking, feel free to submit your question and we will get to these during the Q&A session at the end of their presentation. So yep, now I think Gabe and Alberto, you can feel free to start presenting.
Yeah, no, thank you, Sophia, for the intro. And again, I think just before we get into the topic of today's presentation, let me just say a few quick words about process ecology in our company. Process ecology has been around for just over 20 years here in Calgary. And all this time, we've been supporting the oil and gas sector with process engineering advisory. That's really how we got started. Optimization, new design, debottlenecking, all this type of engineering studies. But we've expanded our activities. 15 years ago, maybe, we started also supporting our clients with regulatory compliance reporting, where again, we're using our modeling skills and software development skills to gather all the data that they generate from all their facilities, process that data and generate those reports that need to be submitted to ensure compliance. And again, all our activity has led us to develop some software tools that allow us to do this way more efficiently and also solve some of the more challenging problems that our clients are facing. Right, yeah, let's go to the agenda for today. Kind of a quick breakdown there. I'll just talk a little bit about the industry challenges, and I'm going to narrow it down to the emissions challenge at this point, and then explain how what we're calling RTX, our solution, can help solve those problems. And then we'll go through some example cases of the insights that we're finding where we have developed and deployed this platform. And finally, talk about potential next steps and opportunities that we see out there. Okay? Great. So industry challenges, I mean, Sophia referred to that briefly just earlier. There's many regarding production optimization, energy efficiency, but we're narrowing it down here for the emissions regulatory challenge. Again, many of you will be familiar with these recent developments. The federal government in Canada announcing a new methane regulation that requires, or one possible path for compliance is continuous monitoring of emissions at these facilities. We also have another example in the British Columbia regulation, where there's a clear requirement for operators to continuously monitor, very specifically controlled tanks. So, different flavors, different types, but same idea. Again, even for voluntary or for the European market, the OGMP2 guidelines, which also require people to perform these measurements or these continuous monitoring activities to make sure that you're compliant and getting to gold standards or whatever else there is. So again, there's a lot of pressure. There's a lot of movement towards this continuous monitoring situation. And what that has done for several years now, if you can go to the next slide, is it's driven a lot of activity in our industry. We've seen a lot of developments in terms of development of methane sensors, like physical hardware that you deploy at the facility, for example, that are getting really good at detecting methane, from different sources. Whether it's fixed sensors, but of course there's aerial surveys, there's drones, truck mounted, you name it. There's a whole range of different solutions out there in the market for physical sensors. Again, they made amazing progress in how good they are in detecting, and yet there remain challenges. This is what we're hearing from our clients. These sensors are getting really good at measuring methane concentration, which then has to be translated into a methane flow rate, into kilograms per hour of methane. So again, there's several uncertainties there. We're also hearing challenges with how weather may impact the accuracy of these measurements, the wind directions, wind speeds, day and night, snow, all these different factors. And again, the other concern that we're hearing is that this typically requires, again, more hardware to be installed at the facilities, which implies, kind of an additional maintenance load, additional point of failure. So again, there's several different concerns. The last one that Sophia also touched on was, there's a lot of value in knowing that there's methane around your tanks or, somewhere in your facility, even quantify how much methane there is based on these algorithms. But then ultimately, the real need is to know why that is there, what's causing that. And that has to be explained with the process understanding and what's happening in the process at that time, and so on. And that's where we see a lot of value, again, like the title says, leveraging all the data that we already have at these facilities available. So that kind of frames it. The other thing that we see, again, in terms of alarms, of course, there's multiple alarms going on at these facilities for, pressure levels, liquid levels, temperatures, all these operating parameters that are used to control the process. And people, operators, engineers, they're already kind of facing a lot of those alarms. And then it's hard to process those, put priorities, which ones to investigate. And because of that, then teams are mostly reactive, right? So time spans, there's an event detected or some situation problematic. And then, they have to pick which ones to investigate in more of a reactive mode. And the other thing that we're seeing is, of course, the teams running these facilities are pretty lean. So again, the availability of experienced engineers that can do all that investigation and find solutions for these events or anomalies, is challenging as well, because these are time-consuming activities. So that more or less wraps up the challenge as we understand it from our clients. And then let me now move on as to how we're approaching this problematic with a different lens, with what we're calling RTX. So in this next slide, this helps me explain how this works. So on the left side, you see you have your facility, your plant is already, have a ton of different sensors, transmitters installed for process control. So that's your SCADA system that is collecting data on temperatures, pressures, flow rates, and you name it, valve openings. So that there's a ton of data that is coming in, pretty high frequency, every 5 seconds, 10 seconds. And of course, people are using this data to control that process on an ongoing basis. And then all that data goes to databases, so data historians. So that's where we see there's a lot of value that probably can be untapped. So what you see here on the green box around there is what we're proposing to do. So it's tapping into that data that's already there. The sensors are already installed. They're already being maintained for process reasons. And now we tap into that data, pull all that data, and feed a process model. Again, this is a high fidelity simulation model. What it does is that it consumes all that measured data and then uses first principles, physics-based, thermodynamics, heat and mass balance, all the tools that we have as process engineers that we've been using for a long time. And it brings all those tools to provide a complete picture. So it fills the gaps. There may be some variables that are important that are not measured specifically. So we can use those methodologies to calculate and fill in the gaps. We can even, methodologies can also help us calculate other KPIs that are simply not measured, things like efficiencies, for example, of equipment. And then we create a very complete picture of what that process is looking like, what it's doing, and that happens at high frequency. In this case, I'm talking about every 10-second data feeds and the model solving every 10 seconds. The other thing, now that we have this big picture and that we know what's happening, let's say across the process, this platform also implements several statistical tools to help us detect anomalies. So now, spikes on specific variables or trends that are happening in the process for some reason, then the platform is going to be able to pick those out and then perform some correlation analysis. And what that means really is that because it has all the process context, now if there's a spike in one of the key variables, then via correlation, we can see what else was happening at that same time at the facility. And with the knowledge of the flow diagram and all these things that we know about at this point, help us identify root causes. Now, at the very right of this image, what we're doing is leveraging AI in the form of LLM models. And just to be clear, we're not asking the AI to run any calculations or to do, no raw data goes there. It's just at the very end of all that analysis that we leverage the LLM or the platform does to generate a good narrative, human readable narrative that is going to explain in relatively simple terms what anomalies have been detected, what are the likely root causes of those happening, and also including potential mitigation actions that engineers or the company can take to minimize or eliminate those anomalies and those deviations. So that's kind of the general concept of this RTX solution. And then, of course, that LLM, it brings a lot of power. Many of you will have had experience already with these tools, and the time savings can be very significant. Again, traditionally, even if I'm able to detect an anomaly and do the investigation, then as a senior engineer, I will go back into my SCADA or my historian, start digging data out for that time period or whatever, and then start hunting for those correlations. That's time consuming. And then on top of that, once I figure out the relationships and the root causes, then need to come up with solutions. With this AI-enabled approach, all that time gets compressed, and now the process engineers can spend more time looking and implementing solutions instead of trying to identify them in the first place. So it's a very powerful technology, and we think we found a great application for this AI together with all the engineering knowledge and simulation that we talked about. Right, next. Okay, so this platform, to date, we've seen different use cases. Some of that can be, very much tailored for what we're calling process, the bottlenecking or production increases or, challenges in production. The other one that's gained some interest is just energy efficiency, identifying when, energy consumption may be trending the wrong way or heat exchangers may be fouling, and then that's causing additional fuel gas consumption, things like that. But of course, the topic of today is more around the emissions use case, which again we talked a little bit in the challenges for industry. So let me just move on with that emissions theme and show you some examples about the things that the platform is able to identify and how this helps industry. This is a particular case study. The platform has been deployed at the Tourmaline facility in central Alberta for, maybe a year and a half now. So we've gained, good experience in this particular site. That's an image of the gas plant. And again, remember, even if I'm more interested in the tank farm, for example, and there's a lot of interest here in Canada on tank emissions, but again, the RTX platform and the model, it really covers the whole facility. Well, all the way from inlet separation, compression, stabilization, whatever configuration you have, it covers the whole facility. And that's exactly the reason why having the whole process context becomes so valuable. Next, please. Okay, so let's be getting to some of those examples. This is a portion or a section of that gas plant that I was showing you. You'll see the gas coming in, there's the inlet separator, and the vapor goes up. The condensate in the middle line goes to the stabilizer, and then the vapors from that separation tower kind of get commingled with the other vapors and go out as the stabilized gas. That's kind of your normal operating conditions. But of course, these facilities are equipped with multiple safety layers, especially around the pressure protection. So there are some configurations here. Next slide, please. So whenever there are some specific conditions, then that valve, following the yellow line, will open, and then we'll start sending gas to flare. Again, that's usually a pressure protection system that ensures the integrity of the equipment and, of course, safety of the people working there. And as an example, in this chart, what we're seeing is, again, RTX is tracking the pressure profiles continuously, right? 24/7, that's always there. And suddenly around, I think it's around 8 a.m. on this particular day, we see an excursion in that pressure. And of course, what that means is that valve opens, now you're flaring. And as a consequence, now the platform is evaluating, okay, what was the duration of that situation, and how much methane was actually sent to the flare or even released to atmosphere with some assumptions on efficiency. And then again, it's tracking continuously and then aggregating, across all these different events that happen at these facilities, to give you a really good picture of where your emissions are coming from, and like we'll see later, why they're happening. The next slide, I have another kind of similar example, different flavor. So on the very left, you see this kind of splitter where a bunch of lines are coming out. This is just your gas going to different compression trains. And if I follow, let's say, one of those trains in my next, you see the gas flow. That's typically what it should do. So it goes to the suction bottle, then the compressor itself, then some cooling, and out to sales. And again, that's normal operation. But again, we see this type of situations relatively frequently at different facilities where, again, at some point, for some reason, now you're flaring that gas. You're opening that valve, and it's now going to flare. And in this particular case I'm describing, in the next chart, you can see that here, the light blue line that you see there is the power to the compressor. So again, based on pressure differentials and all these things, we're calculating how much power is being used by that compressor engine. And then something happens that the power goes down. Power goes down, so the compressor trips. And then, of course, immediately you see the flare. And so again, nothing new or amazing about this behavior. This is how these systems are designed. It's just the ability to track real time what's really happening, and again, why this is happening. This particular case, based on the correlations that I mentioned before, it appears that some liquid carryover could be the main reason for these compressor trips. Right. So again, those are a couple of examples of the insights that you can gain when you're processing your data in the way we're proposing. Next, I think we have a little bit more detailed description of tank venting situation. So I'm going to let Gabe take over here and go over this example.
Yeah, thanks, Alberto. So we've been seeing a lot of attention on tanks lately, mainly because of regulations requiring continuous monitoring on the controlled tanks by 2028 in the BC case, for example. And we wanted to show you our take on how to continuously monitor a tank for emissions. So first off, we're going to start with the problem formulation. What you're seeing on the screen is just a free body diagram of a tank, and it's a controlled tank. So the vapor from the controlled tank goes to a VRU compressor. And usually in the setup, you have access in terms of data to the level of the tank. You have a level transmitter. And on the suction of the VRU, you usually have a pressure transmitter as well. Operationally, those are kind of required for the operator to do their job. So you usually find those there. And the problem that the regulations are trying to address are the two safety devices on the tanks. So the pressure vacuum relief valve, the PVRV, and the thief hatch. Those are there just to protect the tank from explosion or implosion, depending on the scenario. If the pressure reaches a certain point, then the safety device opens and relieves to atmosphere so that the tank integrity isn't compromised. And what we're trying to find is the flow rate of vapor leaving the tank, and specifically the flow rate leaving through the safety devices versus leaving through the VRU. And what RTX calculates in the upstream is the inlet to the tank. So we know exactly what's flowing into the tank, how much, the composition, pressure, temperature, and then RTX models the tanks. So it does a flash in there to get the flashing losses, and it also accounts for the level rising and falling to get the working losses in the tank. And then it allocates between the safety devices. So next slide, we'll see the relationship of these different variables. In light blue, you'll see the tank level. So at the beginning of the day, it kind of starts rising. And in purple, you'll see the pressure in the VRU suction. So the pressure climbs, reaches a certain point. The pressure then decreases, and then it starts climbing again, reaches a certain point. So when the pressure is climbing, that ceiling is your PVRV opening. And then the PVRV relieves the tank, and the pressure starts going down. And then the PVRV closes, and then it continues climbing. So you get this bit of a chattering behavior, and that ceiling can be the PVRV set point. There's even a case in this data at 12 p.m. where the PVRV wasn't enough to relieve the pressure, and it kept climbing. And then you had your thief hatch open, and so you have the thief hatch set point at that point. So it's a very physical phenomena. The safety devices have a weight in them, and if it reaches a certain pressure, then that weight gets lifted. It's very physical, very deterministic. Next slide is what RTX calculates. So every time the safety device opens, we calculate a flow rate from the safety device based on physics, based on modeling the tank itself. So next slide, please, is, okay, we've identified an event, but can we actually tell you why that event occurred? And in this case, we have a water tank that has vented, and it's due to the pressure in orange. And RTX, because it sees all the operational data, can help you figure out and start investigate this event. So we can look at the level in the tank, see that the tank is being filled up. Then we can look at what's coming into the facility, so how much water is coming into the facility. This one's a bit harder to see, but you see there's a bit of a hump starting around 11 a.m. and then ending at 1 p.m., where you have a greater flow rate for the normal. So a slug is coming into the facility at that time, a slug of water. And then lastly, we can look at the temperature of the inlet separator just to see if that slug is overwhelming the process. And we see that the inlet heater is not able to keep up with the demand, the heating demand on that water because it's February 14th, it's quite cold outside. So we went from not only event detection to quantification and root cause analysis. And then we took it one step further. For the entire month, we decided to see how many of these events we saw, and then how many liquid slug events, if we want to call it that, we saw. And the finding was that 40% of the time when we saw venting from the tank due to pressure spikes, we saw a liquid slug coming into the facility, be it a water slug or a condensate slug. And we also saw that the condensate slugs were more important than the water slugs in terms of lifting the devices, which is a great finding we took back to the operator, and the operator was surprised. He said he thought it would be more like 80%. So it's a known issue for the operators, these slugs coming into facilities. Next slide, please. We've been talking about venting, which is a pressure-induced event, and it's very deterministic. Like I said, there are weights on these safety devices. If the pressure reaches a certain level, then the weights must lift. So it's very easy for us to tell you there is an event or there isn't an event. However, we've been seeing also that there's a leaking scenario where your thief hatch usually has a seal that's just not quite that good, and sometimes it's either broken or there's ice forming on that seal, and some gas is able to escape through your thief hatch. And that itself is a lot more statistical. It's things not working as they should. So you expect one thing and something else happens, and then you have to apply statistics to figure out, okay, is this really abnormal or is this within the normal range, so to speak? And what we've done in the tool is we calculated something called the probability of leak, taking into account the theoretical versus actual kind of what we see. And in the next slide, you see that this probability of leak is calculated with time. And in here, we have 3 tanks, the water tank, the condensate tank, and the slop tank. And we see that the water tank is definitely leaking for a long period of time during this month. And the slop tank was leaking, and then it suddenly stopped leaking after some time. And again, we took this back to the operator, and he said that they actually fixed, they replaced the thief hatch on the 29th of June. So that's why we see a lot less probability of leaking for the slop tank. And then the condensate tank, we saw no issues with in terms of probability of leaking. So again, RTX allows us to identify events, quantify events, and perform a root cause analysis. But what if that root cause analysis could be done automatically? And that's where we took it to the next step. Every day, our tool calculates a statistical analysis report. And then that report is sent to LLM to make human readable suggestions and root cause analysis for all the events that happened during that day. So you can think of it as your physics AI process engineer co-pilot that can give you a reason behind every event that RTX is seeing. So your senior engineer, instead of becoming an investigator and going from scratch for each event, they can just become a reviewer and see, okay, that reasoning makes sense, that reasoning doesn't make sense. So let me investigate at that point. So it saves a lot of time for the reviewer and for the senior process engineer. Right, and I think I'll take this opportunity to pass it back to Alberto to talk about what he sees as the opportunity for TX.
Yeah, no, thank you, Gavin. And look, again, even today, we're still exploring different correlations, different metrics that can, we're interrogating the data all the time, and as time goes by, it gets better. It gets better. So again, maybe just to summarize what we talked about today, and then later open up for questions. Just a quick summary. So again, a platform like this, RTX simulation connected to SCADA, supplemented with statistics, and then leveraging AI. We think it's a really powerful platform to support the industry in the emissions case, but like we said initially, it doesn't need to be just emissions. We've seen cases with energy, we've seen cases with production optimization directly. And again, that's time saving that we're seeing in terms of root cause analysis and providing some insights into potential solutions. That's also very valuable. So again, if anybody in the call, if you're interested, if this seems something you'd like to explore further, please reach out. Something that we're proposing that's been working well for some of our clients is again just have an informal chat, right? Like what we call a discovery call, just to see whether this may even be a fit for your facilities or some of your facilities, and then very quickly figure out if there may be an interesting value for your company exploring this solution. If that is the case, then what we're proposing typically is to run this engineering assessment. Again, it could be like a 2-month period, looking at historical data, and then kind of prove the value using historical data before investing too much or spending too much time in the actual live connection and the deployment of the facility. But again, we're pretty confident that you will see the value, and then we can deploy formally inside or in your infrastructure or outside. Really depends on the preference of each company. So with that, I think I'm gonna stop right there, and again, just if you have any questions, please, we'll be happy to try to get as many as we can.
Thank you, Alberto and Gabe, for your presentation. It was very insightful, and there are some very good examples of how RTX is being used currently. It's deployed at 6 facilities so far, so we're keen to see where this RTX will go. I have some questions, some kind of questions that came out of that presentation. I will start with Alberto. Let's see. So what steps are involved in deploying the solution at a facility?
Right. So again, I'm going to make a difference between the initial pilot with historical data that I talked about. But let's say that the value was, proven, and the facility wants to go ahead. Again, the typical flow, yeah, no, this is a good slide for it. So again, usually we start by reviewing PNIDs, PFDs, PNIDs, right? That's what we need to build that model, that simulation, that representation of your plant in the platform. So after that review, we also take that chance to identify which are really the transmitters, which SCADA points are really necessary. Again, there may be many hundreds of data points in that SCADA system. Not all of them are relevant, depending on the objective of the model. So we do a screening. We identify the transmitters. We work with the client to determine other KPIs of interest. And then comes the point of connecting to the data historian. Again, this is now when you have an ongoing solution in place. Again, feeding that data into the platform, whether real time or, we've seen different solutions. Sometimes for emissions, it's not absolutely necessary to be real time. So we've been doing, for example, 1 hour data dumps, for example, at 10-second intervals. And then the results come an hour behind, but that seems to be good enough for that application. And then that's when the real-time tracking and all this analysis starts. So again, this is the typical process. I think the first 3 steps usually would take us, I don't know, maybe let's say 20 hours of work to get to that point. And then the actual connectivity, there's options depending on your own internal systems, whether there's available APIs to historians in a data lake or something like that, or we having gone down the path, the simple path, let's say, of a CSV download from the historian that then the platform can detect and process. That's the example I was thinking about every hour. So this is typically the process that one would follow to get this RTX running.
Great. Thank you for that answer. That's very helpful, especially for the operators in the call right now. I also wanted to comment yeah, if anybody has questions, please feel free to put them in the Q&A box. It's just at the top of your menu bar. We're just gonna go through some of these questions here. Okay, so Gabe, I think I will ask you the next question. So what methodology was used to determine the leak detection probabilities from the tank pressure data?
Good question. I think these are physical events. So in theory, we know what should happen. If your level in the tank is rising, for example, you'd expect the pressure in the tank to rise with it. So you have these relationships that are theoretically defined by physics, by equations, and our tool calculates those theoreticals. And then from the sensor readings, we see the actuals. So then the probability function really is how far are you deviating from theory? And we have a bunch of different relationships that we look at and we give weights to them. And we spit out a single number to the probability of leak.
Yeah, and something, let me add something there, Gabe, because I thought it was very interesting. When we were talking about leaks, again, the relief events were very clear, and they are very clear when you see them in the platform. Leaks are of course, more challenging, and initially we were exploring the pressure. For example, imagine if you have a pressure sensor right in the tank, but it's a noisy signal, and leaks are kind of hidden in there. So it's very difficult to use only one pressure measurement and infer a leak. However, as Gabe was saying, once you start looking at relationships, the pressure in the tank relative to pressure somewhere else, or ratios, the rate of change of the liquid level versus the rate of change of the pressure increase in the tank, those relationships are very sensitive and less, let's say, influenced by noise. So once we start, questioning the data using these type of relationships, then very interesting results can be seen.
Awesome. Thank you, Gabe and Alberto. I will ask the next question here. So, Alberto, what deployment options are available for producers? Can this be provided as a subscription service, or can it be owned and hosted within their own infrastructure?
Yeah, no, that's a great question. And I mean, the reality is that, I mean, everybody has seen it probably, but the world is kind of changing, with all these AI tools and this and that. So of course, initially, and we still do that today, as a subscription model, it is good, where Ecology is hosting the platform, and the data comes to our cloud with all the protections and all these things are required. But we also heard several, clients and operators express, the desire to move away from that kind of software as a service model. And because of that, we're also offering the option to deploy inside the client's own infrastructure. Again, so, we build together, we deploy together inside their infrastructure, and now the platform runs, without a subscription model, really. So we have both options. Again, I think it's pretty much about what are the preferences and the policies at different companies. I think that's an area that's still evolving, and we're responding to that by keeping this flexibility.
Great, thank you. And so here's another question for Gabe. Does this solution rely on AI to deliver its functionality, or can it operate independently of AI?
Yeah, good question. I think the best use of AI we've had is really its storytelling abilities, its critical thinking. not quite its data analysis so much. What we've done in the tool is we've designed it with a kill switch for AI. So it's a single point of contact. Want AI? Yes, no, and that's it. What we do is we perform our process modeling. We then perform a statistical analysis report. So what are the events? When did they happen? What was kind of spikes at the same time as the events, dips at the same time as the events, are two events going together. So this statistical report is what we send to the AI. And it doesn't get the raw data, so to speak. That makes it so the AI can give a lot better answer behind, okay, what do I think is happening? What are the root causes?
Okay, nice. So if a company, for example, is not allowed to use the AI for the tool, they can still use the tool with, experienced process engineer can make the same analysis.
Right.
Yeah, and I think that also adds to my earlier comment about how comfortable an organization may be. First of all, hosting process data in an external cloud, but also accessing AI tools, right? Again, in conversations, there's a whole range of policies and reactions to these new technologies. In some cases, there's absolutely no access and total 100% no to calling an AI for any reason, right? In other cases, we're seeing other policies being more relaxed about which tools can be used and how can they be used. Again, that's all evolving very quickly. So we'll try to stay on top of that and see how we deliver the most value.
Awesome. So yeah, there's a couple more questions here. Alberto and Gabe, I think. Okay, I will ask Gabe. So this is from Jerry. I thought VRU systems are designed to prevent tank emissions. Is your example a case of an improperly designed system, or is the PVRV venting a normal event?
Right, good question. Yes, your thoughts are right. They are designed to prevent tank emissions. That's completely accurate. The reason we see venting, even though there is a VRU, is the VRU is designed for let's say normal operating conditions. But when you get a liquid slug, for example, into your facility, that's not a normal operating condition. So it overwhelms the capacity of the VRU, either the speed at which it can ramp up, or simply the capacity, the power of the VRU is overwhelmed. So the pressure builds up in the tank, and it has to go somewhere. Just so you know, the pressure ranges we're talking about here are very, very small. We're talking about like 7 kilopascals from deviation from atmosphere. So these tanks are really, really important. Like they're really protected against overpressure in a way.
And let me just add something, Gabe, because that's again a great question. I think it also relates to the vintage. I mean, some of the plants that we're working with, have been around for a long time, and the operating conditions, the fluids that they process have changed. So again, maybe it was designed for some rates before, but now it's seeing something different. So that's what the system does to protect itself from overpressure. And also to add to one of my initial slides, because when you have a methane detection, it will be great to know if this methane detection is because of something working well. So again, you want the thief hatch to open, you want the PVRV to open because that's what it's for. So in that case, even if I know that there's methane around, there's nothing really to go and fix in the tank. Again, we see some opportunities to improve things upstream of the tank, but it's not like you need to go and fix something or replace a thief hatch or anything like that. So again, even those distinctions are very valuable to know when to go and repair, when not to go and repair something.
Yeah, great answers, Gabe and Alberto. Here's another question. So is this tool applicable only at individual facilities, one by one, or can it be applied for a system of facilities? So in other words, if you have multiple wells, facilities, and pipelines that connect them, can the whole system be fed into it as a larger system?
Well, that's a great question. I mean, in principle, there's nothing to stop the simulation model from expanding its boundaries, right? So we did have a case where, again, it was valuable to include a portion of the gathering system inside that same model, because then we would be able to check the pressures at the field level versus what was happening in the plant. So again, there's good use cases for expanding boundaries and looking at systems. The one challenge that I'll mention is again accessing the data. You know, if all the data for the bigger system is sitting in the same database, then it's no problem. But typically, you will see different data systems for different portions of the let me call it of the field or of the asset. So again, that's something that can be figured out, but that could add, you know, a little bit more complexity into how you see the whole thing integrated. But again, in principle, there's nothing to stop us from expanding the boundary.
Yeah,
Great. Thank you.
and RTX was designed to handle multiple facilities at once. If you want to connect them, you can export one stream into the other facility to connect them. But you get issues like Alberto was saying with data availability, how often and frequency, how often you're getting that data.
Great, awesome. I think we're running out of time here. So any final thoughts from Alberto and Gabe before we wrap up?
Go ahead, Gabe.
Yeah, I think the thought that comes to mind is the data itself. The operational data is there. Like operators need it to operate. So there's a wealth of knowledge in there. It's just how do you extract it? So with a tool like this, you're able to build a model and extract the insights that you want from that data. It helps the engineer, the emissions team to be empowered by the data itself. And modeling has been around for a long time. So it's tried and tested. The application using real-time data is where RTX kind of steps in and brings you into the frontier of what's capable with process modeling.
Yeah, no,
Thanks,
thanks,
Gabe.
Gabe. I don't know. I think I'll maybe just finalize with some thoughts on around again how the technology, especially AI, is evolving and you know the promise and the hype, and of course it's powerful. But our view and the way we understand things is that you know it's not about throwing a ton of data to the AI and you know okay go find patterns, go tell me what's going on. Maybe that's going to happen in the future. I don't know. I don't think so. But but we're thinking, okay, the best match is you know leveraging everything we know, everything we've been doing for decades, really, around process engineering, process modeling, physics-based, thermodynamics, heat and mass balance. You know all this foundational knowledge that we have and then supplementing that with the power of the AI like LLMs, we really think that that's a good way forward. That's going to deliver a ton of value in the coming years.
Awesome. Thank you. So before we wrap up, just like to extend a big thank you to Alberto and Gabe for sharing their expertise with us today. We truly appreciate the time you've taken to share your knowledge and real-world experience. Your insights are invaluable in our industry, and as it continues to advance continuous monitoring, emissions reductions, and process optimization. If today's discussion sparked any of your interest in the audience, Gabe has also written an in-depth article that explores many of these topics we covered today. It's a great resource if you'd like to dive deeper or have as a reference. So we'll be sending that out in some post-communication emails. And you can also visit our website at processecology.com to learn more about RTX. So thank you all for joining us today. We really appreciate you taking the time to be with us here, and we hope you found this session valuable. If you have any questions or like to continue this conversation, please don't hesitate to reach out to us. And yeah, thank you for attending and hope you all have a great rest of your day.
Yeah, thank you, everybody.
Thank you.
Thanks, everyone.
Bye.